Hello, everyone. I'm delighted to share our research on risk-aware model predictive path integral control using conditional value at risk with you today. This study enhances the model predictive path integral, or MPPI, by making it capable of handling dynamical disturbances. First, I'll begin by providing an overview of the MPPI algorithm, including its problem formulation and any limitations it may have. Second, I'll introduce the concept of conditional value at risk, or CVAR. Following that, I'll discuss the proposed risk-aware MPPI, which incorporates CVAR into MPPI, highlighting both its problem formulation and control architecture. Subsequently, I'll present simulation and experimental results, and engage in a discussion about potential future work in this area. The MPPI algorithm aims to minimize an objective function, given a deterministic dynamical system. To achieve this, it introduces Gaussian noise into a nominal control sequence and generates thousands of sample trajectories through simulations by employing multi-threading on a GPU in real time. The MPPI then generates the optimal control sequence by calculating a weighted average across all sample trajectories. As shown in this animation, the algorithm samples a bunch of trajectories, assign weights based on their cost, and calculate optimal controls. However, since the vanilla MPPI uses a disturbance-free system for trajectory sampling, it does not consider any risk induced by potential noise either from the system or from the environment. In practice, an optimal trajectory generated by MPPI that approaches invisible regions, such as obstacles or track boundaries, may lead to collisions due to unforeseen disturbances. Our research aims to address this issue by enabling the MPPI to account for disturbances. This is specifically accomplished by incorporating conditional value at risk into the MPPI trajectory costs. The value at risk of a stochastic variable x is defined as the value that x has a 1 minus alpha probability of being greater than or equal to, where alpha represents the confidence level and ranges between 0 and 1. The conditional value at risk, on the other hand, refers to the expected value of x beyond the value at risk. In other words, CVAR describes the expected value within the worst 1 minus alpha quantile of the distribution of x. In light of this, the proposed risk-aware MPPI, or RAMPPI algorithm, addresses the following problem. While maintaining the same objective function as the original MPPI, it also employs disturbed dynamics to sample and evaluate the CVAR value for each MPPI sample trajectory. RAMPPI then leverages the CVAR value as a filter, substantially diminishing the weights of high-risk sample trajectories. As illustrated by the following animation, the RAMPPI algorithm initially samples trajectories using a disturbance-free system. For each of these trajectories, it further samples additional trajectories using disturbed dynamics. The CVAR is then assessed using these disturbed samples and utilized to update the cost of each disturbance-free trajectory. Consequently, the RAMPPI produces controls that avert disastrous control scenarios, such as collisions. Let us take a look at the cost mechanism behind the scene. When the variable x is deterministic, the cost cannot sense the potential dangers induced by disturbances. The dashed curve shows the cost profile. However, if x is stochastic, the CVAR evaluation process captures the worst-case scenario and alerts the controller that getting too close may be risky. As we increase the confidence level alpha or reduce the upper bound CU in the CVAR constraint, the same distribution suffers from more severe penalty, thus pushing the random variable x towards safer regions. We carry out simulations and experiments on an autonomous racing platform using different types of noise. On average, the RAMPPI outperforms the baseline MPPI in terms of collisions. Moreover, we use different alpha and CU values for RAMPPI and compare the resulting performance. From the heat map, we see that RAMPPI tends to perform better with high confidence level and smaller CU. To validate the proposed controller's real-world performance, We also run experiments on the real car. The autonomous vehicle experiences real-world disturbances, such as control delay and inaccurate model, which causes the wiggling maneuvers in the video. We can see that the MPPI frequently collide with the boundaries. The MPPI achieves approximately the same lap time, while significantly reduces the number of collisions. In the future, we can integrate other risk metrics, including chance constraint and time-consistent CVAR modifications to the proposed control framework. We can also improve the algorithm sampling efficiency by integrating covariance steering in the trajectory sampling process inspired by the covariance-controlled MPPI. That's all for my presentation. Thank you.